All right, let us now continue with the next algorithm, which is Grover's algorithm. So this algorithm is also one of the most famous algorithms, and it's an algorithm that is searching an unsorted database. That has n equal to 2 to the power n different elements. And it can actually do so in square root of n time, which is faster than any classical algorithm, because it can actually even be proven that a classical algorithm needs on average n over 2. So scales with n time. So an example is you can think of a phone book. That's a common example that people give, where instead of a phone book is sorted by names, right? But if instead of giving you a name and asking you what the phone number is, I could give you the phone number and ask you what is the name corresponding to that. That would be an unsorted database because it's just not sorted by phone number. But if you go look through all the different entries, it will on average take you n over 2 time to find it. However, now an important thing with Grover's algorithm is that the example I just made is a very illustrative example, so everyone, like, it's very common to give this example. However, this is not really a good example because in an actual implementation, again, we need an oracle in the end that implements our function that can evaluate whether or not some function solves everything that we want. So in the end, what we can do is we can construct an algorithm that finds some element where we say, for example, we have a function that returns f of x equal to 1 if it is the element that we're looking for, and it returns f of x equal to 0 if it's an element that we're not for all the other elements. Now, within the example of phone book, we could say, okay, the correct name would be the one that returns for x being the correct name, we would return f of x equal to 1. However, this implies that this function that looks through all the different phone numbers, that you would first need to give this function the whole full phone book. And if you anyway need to put all the numbers of the phone book into that function, then in the same time you could already just have looked it up. Like, this does not go any faster. So the problem is a bit of how to implement this oracle. And now we're back to the point that I made before, where I said, okay, we cannot just say, oh, we do have an oracle that can do everything we want, and then this simplifies, and that's how quantum algorithms give us a speed up. No, of course, this should not be the case. But what we can do, for example, is we can solve some satisfiability problems. Some problems that are efficiently solvable by a function, where we can say, for example, we want this and this and this and this condition to be satisfied. And then the function can efficiently check whether all possible requirements are satisfied. And if this is the case, it returns 1, otherwise it returns 0. However, if we now have exponentially many different inputs, it could still, then a quantum oracle, like some quantum, if we implement it on quantum systems, we could still have a function that efficiently checks on all elements in superposition, whether or not they satisfy all the requirements. And this is then a problem where we could actually get some speed up. So things you could, for example, think about solving a Sudoku. If I give you some solution, you can check whether it satisfies everything, whether, like, you have every number in each row and each line and each column. But you cannot, but it would take you so many, you would need so many different tries to, like, go through all the different possible combinations. And then here, this is where our oracle could just check, is it valid or not, efficiently, and we can somehow, using quantum systems, input already a superposition of all different solutions, basically. So this is the main idea behind it, and that's why it's important that, yes, you can think of the phone book example, but you just need to make sure that this is actually not a suitable example, because that's not something that could be implemented easily by an oracle. That would not take longer than classically. But okay, in general, we just now call it a search algorithm, and we want to find some element w, which may be a solution to a satisfiability problem or a name in a phone book, whatever. And we again an oracle UF, again a face oracle as we defined earlier, with a function that takes n bits as input and outputs either 0 or 1. And then we would get f of x would be 1 if x is the element we're looking for, and it would return 0 in the other case. Also, we actually we'll use later another function which I call f0 of x, which can also be efficiently simulated because it's not actually an oracle. It does not depend on w at all, but it just is a function that returns 0 if the input is just a 0-bit string, and it returns 1 in any other case. So if we now want to implement, if we now check what UF does, so the unitary, it turns W into minus W, because we said UF is the face oracle, right? So we get a minus sign if we are in the W state. While for any other state that is not the W state, it will just have the face 0. So we will just return X again. X that are unequal to W. This means we can rewrite our function U so that we can write it in matrix form as an identity matrix minus 2 times W. If we now see, if we project it onto the state W, we just get W minus 2 times W, so minus W. While if we project it onto X, if we apply to any state X that is not W, the second part would be 0 because it's orthogonal. All the X are orthogonal to W, and we would just get X. So that's what we want. And now analogously, we can do it for UF0. Here we want that the state 0 to the power n stays as 0 to the power n, because there we get the face 0. While any other state actually gets the minus sign in this case, with all x that are not the 0 state. And in this case, UF0 can be written as, analogously, 2 times that state 0 minus identity. So let me give you the quantum circuit of Grover's algorithm. We start, as always, in all qubits being in the 0 state. Then we apply a Hadamard gate on all qubits. Then we apply our oracle function, UF, the one that depends on W. Then we apply another round of Hadamard gates. Followed by the other oracle, the one that is independent of W, so UF0. Some more Hadamard gates. And finally, we do a measurement. Or then the output is just some state y. It is a bit string consisting of n bits. However, what we actually also do is we repeat this whole cycle here r times, where r depends on our number of qubits. You will see that later. We'll define r later. And everything that I colored here in purple We'll give it a different name. We'll call it V. So the claim I make in this case is that Y, so our output bit string that we measure, equals W, the element we're looking for, with a very high probability. And for the proof, we will first need to define some states. So let's start with defining the uniform superposition state. So we have here, after applying Hadamard gates to all states in the zero, to the zero state, we get what you call the state S, the uniform superposition. So it's just Hadamards on all qubits applied to zero. And this equals, you've seen it before, 1 over square root of 2 to the power n, the normalization factor, and then the sum over all possible bit strings x in 0, 1 to the power n. And then we also want to define V, which I just illustrated here in purple, which equals Hadamard gates and Hadamard gates times the unitary UF0 times again and Hadamard gates. And we can simplify that a bit, because for UF0 we said before here that we can just rewrite it as 2 times 0 to the power n minus identity, and I'll just write this in 2 terms then. We have this first term minus the second term where we have times identity times Hadamard to the power n. And all Hadamard applied to state 0 just gives us the state S. And then also from the right side on the bra, again, Hadamard is acting on state 0, give us S, so we just have 2 times the projection onto S. Minus, and here identity does not have any effect, so identity times Hadamard is just Hadamard, and Hadamard times Hadamard actually also gives us identity, so we just have 2 times S minus identity. So summarizing what we can do, say what Grover's algorithm does, if we look at the quantum circuit and at the definitions that we just did, Grover's algorithm carries out the operation V times UF to the power R on the initial state, or on the superposition state that we prepare in the very beginning, S, and to the power R because we're repeating it all R times. So now we define, to another definition, we define sigma to be the plane that is spanned by S and by W. So S by our superposition state and W the element that we're looking for. It's just 2 arbitrary, it's just 2 vectors in the, well, in the big Hilbert space, but we can always say that they span a plane. They don't need to be orthogonal for that, of course. They are actually not. And then we let W orthogonal be the state that is orthogonal to W and that lies in sigma, because there's, in such a big space, there's of course infinitely many vectors W orthogonal that are orthogonal states, there are infinitely many states that are orthogonal to W, but so W orthogonal is supposed to be the one that then lies in this plane. And we'll define it by W orthogonal. It's 1 over square root of 2 to the n minus 1. Times the sum over all W, over all x except for W, x. So we have the equal superposition of all states except for W, which lies in the same plane but makes it orthogonal to W. Now we can rewrite S in terms of W and W orthogonal. We can rewrite it as 2 to the n minus 1 over 2 to the n, that's just the normalization factor that we need, times W orthogonal, so that we have 1 over 2 to the n weight on it, plus 1 over 2 to the n times W. So here we have 1 over 2 to the n weight on all different states, squared, of course. And we define this now as cosine of theta over 2. So the first term times W orthogonal plus sine of theta over 2 times W. We can do that because you know that this part squared plus this part plus squared gives 1. So we can just choose any angle theta, or define it that way, such that this holds. So we defined theta such that sine of theta over 2 equals 1 over square root of 2 to the power n, which means that theta is defined to be 2 times arc sine of 1 over square root of 2 to the power n. Good. These were just some definitions that will simplify our algorithm given by this quantum circuit here by a lot. So the protocol that we have is basically 3 steps. The first step is we prepare the state, the superposition state S. That's what we do here in the green part. Then the second step is we apply the unitary UF, oracle, phase oracle, which is identity minus 2 times projector of W. And then in a third step, we apply V, which we said can be rewritten as 2 times projector onto S minus identity. So if we can actually, let's plot how that looks like to illustrate the algorithm. And let's say we have our state W, and this is the plane sigma. So this would actually be then our state W orthogonal in the plane sigma, orthogonal to W. And then if we apply, and then if we prepare in the first step, if we prepare the state S, this will be quite close to W orthogonal. We know that this angle here is theta over 2. So let's from the definition of S, we can see it's cosine of theta over 2 times W orthogonal plus sine of theta over 2 times W. So yeah, you can just plot it here. Now the second thing that we do, the second step, where we apply identity minus 2 times projection onto W, well, let's look what happens. So if we first apply identity basically, so applying identity to this vector will stay here. But then we subtract twice the projection of S onto W, which is basically this part here. So this would correspond to the inner product of W and S. It's just this. And we go 2 times this inner product into the minus W direction. Minus W direction would be down here. So we go twice this amount to the minus W direction, so we end up here. So here is UF times S. So this is where we actually end after the second step. So we again will have the angle of theta over 2 here. So what this second step corresponds to is actually a reflection at omega orthogonal. And this will always be the case no matter where we are. It will always be a reflection at omega orthogonal. And then the third step, it's very similar. It will actually, if you look at it carefully, you can see that this is a reflection at S. So by going up this way, we actually just go up twice the angle and end up somewhere here. So we have an angle of theta here as well. And this will then be the state V times UF times S. So if we apply V times UF, we first go, well, we can see in the beginning we go by theta over 2 angle back in the opposite direction, and then we go basically by 2 theta in the other direction. So what it corresponds to in the end, applying both unitaries, always corresponds to a rotation by an angle theta. So if we apply it again, we would move by another angle theta up here, if we apply both unitaries, and so on. Until we then, at some point, get close to W. So after our applications, I told you before we're going to repeat V and R in total R times. So after our applications of the second and third step, the state is then rotated by R times theta. So this is now how you can see how we choose R. I didn't specify that yet, just that it depends on n. But so we choose R such that ideally we want that R times theta, the angle that we moved on, plus theta over 2, because that's the angle that we start with when we prepare S. That should ideally be pi over 2. Because you want that to be, this angle here would be pi over 2, right? It's a right angle. Of course, this in general cannot be satisfied exactly, but we can still solve it for R. So R should ideally be pi over 2 theta minus 1/2. And now we can insert how we defined theta. We defined it as 2 times arc sine, so we get pi over 4 times arc sine of 1 over square root of 2 to the power n minus 1/2. And now if we assume that n is large, which quantum algorithms become very useful if we have a large number. If we just have a very short set, then we can just classically look for the solution. But so for large n, this scales as pi over 4 times square root of 2 to the power n, which means it goes as square root of capital N, which equals 2 to the power n. So this is where we get the advantage, because I told you in the beginning, Grover's algorithm needs only O of square root of n time, while a classical algorithm would need O of n time. However, now I told you that the claim was actually that we reach W with high probability. Now the question is, how high is the probability, at least? Because the problem, as you can tell, is that, well, this R, we cannot solve it exactly, or usually the R has to be an integer, but in general, if I look at this formula, pi over 2 theta, that will in general not give me an integer. So after R calls to the oracle, the final measurement will result in state W with a minimal probability. And now let's check what the worst case is. So the worst case would be the case where we rotate, and then we have here this angle in the end of theta over 2. Because every time we rotate by theta. And we want to get as close as possible to that line. In the worst case, we would just have theta over 2, so that if we rotate one more time, we're not getting any closer. And in that case, if this angle is theta over 2 between here, so that would be the W state and the W orthogonal state, then the probability that it collapses onto W would be 1 minus the probability that it collapses onto omega orthogonal, which is sine squared of theta over 2. But what's theta over 2? We can actually now use the way we defined it before. We defined sine of theta over 2 as 1 over square root of 2 to the power n. So this just gives us 1 minus 1 over 2 to the power n. So it tells us that actually, even the larger we choose our n, the more elements we have, the more likely we will be to get the right solution in the end. Higher chance we will have. And yeah, this proves the claim that I made before, that with a very high probability, at least for large n, we will reach the state that we would like to reach. So the main principle behind Grover's algorithm is what we call amplitude amplification. And it's something that was not that clear yet, I guess, from the way I described Grover's algorithm by now. But I would like to show you another illustrative way to understand Grover's algorithm, where you can see what this amplitude amplification actually is. So the general idea behind Grover's algorithm is exactly this. Oops. Sorry. Amplitude amplification. For that, let us actually have a look at the amplitudes. At each of the steps in Grover's algorithm. So we have the first step in which we prepare the superposition state, S. So that state where we apply Hadamard to 0 on all qubits. And we'll just look at the amplitude now. I told you in general the amplitude can actually be any complex number, but for now it's only going to be positive and negative numbers, so we can just plot it in 2D, which is nice. So we'll have the different states, 0, 1, and so on. Then we have our wanted element somewhere, W, and then we have all elements until n-1. And here we have the amplitude. And now if we plot if we have the superposition state, then we know this state is given by 1 over square root of 1 over square root of 2 to the power n times an equal superposition, so sum of all these states. So they all have actually the same amplitude, and the amplitude for all of them, so it's going to be the same for all of them, and it's just going to be 1 over square root of n. Then let's look at the second step. In the second step, we apply the oracle, the phase oracle UF, to our state S. Get identity minus 2 times projector V, W, apply to S. And okay, let us now see what happens once we apply the phase oracle to our state. What happens then to the amplitudes? So we have here identity minus 2 times projector to W, applied to state S. And so what this actually corresponds to is, well, we see that if for all the other states, if we don't have the state W but any other state X that is not W, nothing happens. So the amplitude just stays the same as before. So for the state 0 and 1, we have the same amplitude as before, but then for the state W, we actually get minus. So we flip the amplitude for that one. And all others are just the same. So this corresponds to flipping the amplitude of W. So as before, the amplitude here is 1 over square root of n. And now for this state, it's actually minus 1 over square root of n. For the state W, and here all the way until n-1. Then in a third step, the one where we apply V, this actually corresponds to reflecting the amplitudes about the average amplitude. Let me quickly show you why this holds, just for those who are interested in the details. If not, just skip the next 2 minutes and then just look at the plot. So just for those of you who are interested in that, we have psi which is the sum, just take any state psi, that is the sum over some amplitudes times state. So this is just a general pure state. So for all such psi, in this case, then v times psi then yields for any psi that we have 2 times projection onto S minus identity times psi, which is 2 times 1 over n times the sum over all j, sum over all k. Okay, so this is just the superposition state. So I got the normalization factor 1 over n, and then I have, because both the kets can be written as sum over all jj, and the the bra is written as sum over all k. And then a bit more space here. So this is the corresponds to the S applied to the state psi, so times the sum over all I alpha I minus just identity applied to psi. So minus the sum over all I alpha I. Now this, let's rewrite the first part. We have here the sum over all k alpha k. Because for all, if we sum over all I and k, we have the i's, if we sum over all i's, the I is only, we have the inner product of k and I, and this is only 1 if I equals k, while it is, otherwise it's 0 because all other states are orthogonal. So we can just basically replace this part by saying alpha k times k, and then this just gives alpha k. So here we have twice the sum over all k over n times the sum over all j minus the second part, which is just this. Or we can actually also, because it's just dummy indices, we can just change the indices here as well. So we get, rewriting this, let's look at what we have in the first term. This is exactly the average alpha. So we have 2 times the average alpha, right? The average alpha is if I sum over all alphas that I have, and I divide by the number of alphas that I have, I just get the average alpha. And then minus alpha j times ket j. And while this part here corresponds exactly to here, I think much easier to see that this corresponds to a reflection of alpha j about the average alpha. Maybe, in case this is not clear yet, let me give you one more way to show that, because let's say if alpha j equals alpha plus some delta, then alpha j prime would in this case be 2 times alpha minus alpha j. So I mean, with alpha j prime, I mean, once I applied v to that amplitude, I get 2 times alpha minus alpha j, the expression that I just wrote, which would then be exactly average alpha minus delta. Because delta can be written as just alpha j minus alpha, right? Minus average alpha. So before I had, so having some amplitude alpha j, which is average alpha plus delta. If I apply v, I'm getting this expression, so I'm getting average alpha minus delta. So I've exactly reflected alpha j about the average alpha. Sorry, that was now a long mathematical description. Sorry for that. Now you can start listening again if you were not too interested in this detail. I just wanted to give it because for me I was always a bit wondering, like I knew people were saying, oh, it corresponds to a reflection of the amplitude, but I didn't really know why. So at some point I did the calculation and I thought I'd just share it with you because we anyway have enough time, I believe. So what this means for our amplitudes is we have the amplitude 0 and 1 and all of those until then we have the w, the element that we're looking for, and we have n minus 1. And now we should consider what actually our average amplitudes were. So here, in the first step, okay, it's very simple. The average amplitude here was just 1 over square root of n, of course. Now in the second part here, because we flipped the amplitude of the winning element, the average amplitude slightly decreased. And so the average amplitude here is actually 1 minus 2 over n. That's 1 over square root of n. Still very similar. Now if we flip the amplitude around the average amplitude, let's draw the average amplitude with something like this. And then of course this does not change if we just flip around it. The average stays the same. So the average is still 1 minus 2 over n. So 1 over square root n. But now all the amplitudes change. So instead of being slightly above the average, they will be slightly below the average. Except for the winning element, which was before down here, and which will now be somewhere up here. And we'll actually have an amplitude now that is like 1 over square root of n times 3 minus 4 over n. The exact amplitude is not that important. Importantly, we see that this boosts our winning element's amplitude by a lot, while everything else slowly decreases. So if we now repeat step 2 and 3, the amplitude increases even further. This is why we call it amplitude amplification. So in the next step, we would again do step number 2. So we would again flip w to be even further down. Then we would decrease the average even further. Then we would reflect around the average, and so on, until at some point the average is basically at 0, almost. Yeah, so this is another way of seeing how Grover's algorithm works with the R steps, and how it works by decreasing further and further. So one last thing that I want to mention, though, for Grover's algorithm is the case of multiple marked elements. So with a marked element, I mean like a winning element, an element that satisfies all of our conditions. There could be multiple of them, right? So let's see how Grover's algorithm performs then. Suppose we have m marked elements. M marked elements that we call now wi. Then we define the winning state as still as w, but it's not just the state w as before, but now we define it to be the equal superposition of all m winning states. And corresponding to that, we have the orthogonal state, W orthogonal, which is then defined as 1 over square root of n minus m times the sum over all elements x, superposition, except for the winning elements, the m winning elements. The superposition state is the same as before. However, if we now want to write it in terms of W and W orthogonal, it turns into n minus m over n as normalization factor times square root of times the state W orthogonal plus square root of m over n times W. We can easily verify that this gives us the equal superposition state, and so we again define this to be cosine of theta over 2 and sine of theta over 2 respectively. So in this case now, it's just the angle theta has changed, because sine of theta over 2 is not just 1 over square root of n, but it's actually now square root of m over n. Which means that the angle theta becomes larger. And therefore also r changes, the number of repetitions of step 2 and 3 that we need to do, because it goes as 4 times arc sine of square root of m over n, or minus 1/2, which is not so important for large n, of course. And this then scales as square root of m over n. Square root of n over m. Which means that for larger m, we actually need less repetitions, which makes sense because every time the angle is larger. So we start, if we look at the illustration with the angles, we can see that we start again in the superposition state, but every time the angle is just larger, so we need less repetitions to get to the state W. And then we can also see that if we look at the amplitudes, so the first step, if we now look at the amplitudes here, we have 0, 1, and so on. And then we have W1, and let's say we have here W2, and potentially some more W's. And finally n minus 1. So the first step, of course, it looks all the same. But then in the second step, well, now we flip not only one amplitude, but we actually flip all of the winning elements' amplitudes. So we have the amplitudes here that stay the same of most of the states. But then we have those of the winning elements that will be negative now. So here would be W1 and W2 and so on. So this will still be 1 over square root of n. And here we will again be at minus 1 over square root of n. Which means that now the average amplitude actually decreased even further, because we have multiple negative elements, right? So the average will actually be 1 minus 2m over n times 1 over square root of n. So you see, the higher the larger the m, the smaller the average. And this then obviously changes also what happens in the third step. is then in the third step, now that we reflect around the average is now somewhere here. If we reflect, then since the distance to the average is larger, these elements will be even smaller, have an even smaller amplitude than they had if we only had one marked element. So it will actually be 1 over square root of n times 1 minus 4m over n. While the winning elements will be boosted to, let's say over here, omega 1 and omega 2. It would be 1 over square root of n times 3 minus 4m over n. So they will, of course, have also smaller probable amplitudes each, but then since it's even enough for us to find any of them, we're happy to find any of them. The goal is not to find all of them. The goal is to just find one solution that satisfies all conditions. But you can see that the solutions that we don't want decrease just much faster. So adding the two up will go much faster. And okay, something I didn't mention before, but I hope this is clear, is that the amplitude corresponds directly tells us how the probability is to measure the winning element, because the amplitude squared, or the absolute value of the amplitude squared, gives us the probability to measure the element. That's why decreasing the amplitude means that we cannot, if we go down here, we have basically no probability to measure that state. Well, if we have a very large amplitude, this will correspond to a very high probability to measure that state once we do a measurement. But yeah, so with more marked elements, as one would also expect from the classical case, it's easier to find a solution if there are more solutions. So yeah, we will have some speed up, but still it will go as square root of n over m, so it goes still much faster than the classical algorithm. All right, that was it for today. Thank you.